This video is on Hashtable, its implementation, and the time complexity of its basic operations. Here's a roadmap of what we will cover. In this video, we will explore where hash tables are useful and how hash functions work. Let's get started. So where hash tables can be useful? A hash table is a unique data structure that supports fast data insertion, deletion, and searching. More than that, a hash table allows you to store and retrieve related pieces of data efficiently. Imagine that you have a collection where each item consists of two parts. One part that identifies it, like a name tag, while the other part that holds the actual information. This structure is known as key-value pair, and hash tables are designed to organize and look up these pairs quickly. A hash table is also handy when it comes to dealing with data duplication and uniqueness verification. So whenever you need to perform frequent searching on existing data, demand speed in data insertion and deletion, or have key and value pairs, you should think about using a hash table. Okay? To learn more about hash tables, you need to start by learning its core first, the hash function. Before getting to the hash function, let's define hash tables formally first. A hash table is a data structure that is used to store key-value pairs for fast data access, and it uses a special function to convert keys into indexes, which are used to determine the positions of where values are stored. A hash table is so efficient and its basic operations such as search, insert, and delete typically run on constant time. This special function that we mentioned is the hash function. Let's use an example to help you understand what a hash table is and how hash functions work. As you can see on the screen, this is the setup of a hash table. It is composed of two arrays. The first array is used to store the keys, while the other is used to store the values. The indexes of the two arrays correspond to each other. For example, index 1 in the array representing keys correspond to the index 1 in the array representing values. If you have a key and value pair data, it will store the key at a specific index, and the corresponding index in the array representing values will be where you store that piece of value. Okay? Let's try to add some data into this hash table. For example, we have a set of key and value pairs like this. Each pair takes a row, and the data comes prior to the comma represents the key, and the data comes afterward represents the value. Imagine that we are running a big farm, and we have 5 cats, 2 dogs, and 3 foxes on the farm. So we are going to store such information into a hash table. To store the first key and value pair into the hash table, it will convert the key to a numeric value representing indexes. How do you do that? It will use the help from a hash function. For example, the hash function for this hash table is like this. It sums up the digits corresponding to each character, and then divides the sum by 11 to get its remainder. Just in case, there's a correspondence between each character and a number if you look up in the ASCII table. Based on that, we can compute the position of cat, which is 5 because the capital letter C corresponds to 67, A corresponds to 97, and T corresponds to 116 in the ASCII table. When you add them up and divide the result by 11, you will get the remainder as 5. The 11 here represents the size of both arrays. If you want to insert some data somewhere into these two arrays, you need an index that's smaller than 11. That's why the hash function is designed like this. Now you have the index for this pair of data computed. You can move to store it into the hash table. The cat is the key, so it goes into the array representing keys. The number 5 is the value, so it goes into the array representing values. Both are stored at the same index of 5. Next, you will move to the next pair of data, which has the key as dog and the value as 2. When you use the same hash function to compute the corresponding index of the key, you will get 7 in the end. So you will store this pair of data at the index of 7, like this. Next, you will move to the last pair of data, in which the key is fox and the value is 4. When you use the same hash function to compute the corresponding index of the key, you will get 4 in the end. So you will store this pair of data at index 4, like this. When it comes to searching for this pair or any other pair of data, you only need to have the target value going through the hash function to know its corresponding index in the hash table. After that, you can compare whatever is stored in the hash table, or say the arrays representing the keys, to the given target. If they don't match, it means that the target is not in the hash table. With only 3 pairs of data, everything seems perfect. What if we try to insert another pair into the same hash table? In this new pair, the key is ant, and its value is 1000. When you apply the same hash function to the key ant, it will compute its corresponding index as 5. However, in the same hash table, index 5 is already occupied with the pair of cat and the number as 5. So you can't store this new pair of data, ant and 1000, into the same hash table anymore. This issue is known as collision. A lot of efforts are dedicated to addressing the collision issues in hash table. Maybe the first thing that crosses your mind is whether a better hash function will get the job done. For example, we can improve this naive hash function that we have been using from this to this. The improvement that was made is all about here. Before you sum up the digits corresponding to each character, you can multiply them by the corresponding index of each character in that given word. Theoretically speaking, this hash function is a bit more complex and can help reduce the chance of collision, yet it doesn't fully address the problem. For example, when you start using this improved hash function, the indexes of the 4 pairs will end up as this. As you can see, you still have a collision. This time, the collision is between another 2 pairs, cat and a dog. Depending on which pair is inserted first into the hash table, the other pair won't be able to fit in. As you can see, improvements to hash functions don't fully address the collision issues, so we need a different approach to solve this problem. That's the topic of the next video on hash table. Now, you understand where hash tables can be useful and what a hash function is. The next step is to learn about how hash tables handle collisions. In the next video, we will dive into one way to address collisions, open addressing, and we will use it to implement the basic hash table operations.